At first glance, it may seem like a simple condiment, but Himalayan pink salt is much more than that. Its pink hue is captivating, its price is surprising, and its presence in spas, gourmet kitchens, and wellness boutiques has transformed it into a global symbol of luxury and purity. What's surprising is that, chemically, it is 98% identical to conventional table salt. So why can it cost up to 30 times more? What's so special about it? Some claim it has healing properties. Others denounce it as a marketing ploy. But what no one can deny is that its origin is absolutely fascinating. This salt was formed over 250 million years ago, trapped underground since the age of the dinosaurs. Today, hundreds of thousands of tons of this ancient mineral are extracted each year from a mine in Pakistan, worked with near-surgical precision, and then transformed into sparkling crystals destined to illuminate shelves around the world. But how does this journey really unfold? Who is behind that pink glow that intrigues us so much? Stay tuned as we uncover the long and surprising journey of the planet's most famous salt. The story of Himalayan pink salt doesn't begin in a luxurious kitchen or a health food store. It began more than 250 million years ago, when vast primordial oceans covered what is now South Asia. Gradually, these seas evaporated, leaving behind enormous layers of salt, which were then buried by tectonic movements and geological pressure. This is how the oldest and purest salt deposits in the world were created. Contrary to what its name suggests, this salt is not extracted directly from the Himalayas, but from the Khewra Mine in Pakistan, located more than 300 kilometers from the mountain range. There, in an underground labyrinth of more than 40 kilometers of gallery, lies one of the most impressive deposits on the planet. It is estimated to contain nearly 6.7 billion tons of salt. Its discovery, however, is almost legendary. It is said that in the 4th century BC, the horses of Alexander the Great's army licked the pinkish rocks in the region, revealing this buried treasure. This episode marked the beginning of a 1,000-year-old relationship between human beings and this salt. For centuries, local populations have mined it on a small scale, using it as a preservative, currency, and traditional medicine. But it's only recently, with the rise of global trade and wellness trends, that pink salt has become a cultural and commercial phenomenon. Its distinctive color comes from low concentrations of iron oxide and more than 80 trace minerals such as calcium, magnesium, and potassium, although they only represent about 2% of its total composition. These are the things that give it its unique color and its reputation as a healthy salt. Yet, beyond its chemical properties, what truly makes it valuable is its history. A fossil from a vanished ocean, compressed over millions of years, preserved intact under tons of rock, is now extracted by hand in one of the most extreme environments on the planet. It's not just salt, it's living geology, a relic of the past that today graces the landscape with its mysterious splendor. Hidden in the arid landscape of northern Pakistan, at the foot of the Punjab Hills, lies an underground marvel, the Khewra Salt Mine. It is the second largest in the world and has been operating almost continuously since its discovery over 2,000 years ago. From the outside, it looks like a simple industrial complex, but stepping through its entrance reveals a vast labyrinth of pink tunnels, extraction chambers, and galleries stretching more than 40 kilometers below the surface. Every day, around 500 miners descend to a depth of 300 meters to extract blocks of salt that have lain there since long before the continents as we know them formed. Unlike other mining industries, speed and volume are not paramount here. The process is meticulous. Small cavities are first drilled into the massive salt walls by hand or with heavy machinery. Then, explosive charges are placed with surgical precision. The detonation must release the blocks without altering their crystalline structure. The process resembles a medical operation more than an industrial operation. Each explosion releases enormous blocks weighing between 50 and 200 kilograms, which are then transported manually or on small wagons to the surface. The purest and most translucent pieces are reserved for gastronomic or decorative uses, while those with impurities are used for industrial purposes. Working conditions are harsh. The temperature hovers around 30 degrees Celsius. The humidity is oppressive. The air is heavy, and every movement requires considerable energy. The miners work for hours without seeing daylight, armed with hammers, drills, and impressive endurance. Yet the mine is very much alive. Some of these oldest galleries have been transformed into tourist attractions, housing salt car structures, mosques, statues, and even a small train running through part of the tunnels. And despite an annual extraction of nearly 400,000 tons, barely 1% of the deposit has been exploited. This treasure could last for several more centuries. Now that we've seen how this ancient salt is extracted, let's look at the next step, its transformation into a luxury product. Once the blocks of salt are brought up from the depths of the mine, a completely different process begins. The transformation from raw material to refined product. But before shining on store shelves or restaurant plates, each fragment of pink salt undergoes rigorous inspection. It all begins in the open-air storage areas, where the blocks are stacked in huge piles. There, an initial visual inspection separates the lighter, more transparent pieces, intended for consumption, from the darker or more imperfect blocks, reserved for industrial or decorative use. The selected blocks are then transported to the processing plants. Unlike other chemically refined salts, pink salt undergoes a more natural process. It is first washed with pressurized water to remove dust, chips, and extraction residue. This washing is carefully controlled to prevent the water from dissolving the crystals. Then, it passes through vibrating sieves that filter out the remaining impurities and sort the salt according to the size of the pieces. This is when its aesthetic metamorphosis begins. The largest blocks are crushed into smaller fragments, then reduced to fine, medium, or coarse grains, depending on their destination. Technology plays a key role here. Optical scanners analyze each batch to verify visual purity and color consistency. Only crystals that meet the strictest criteria are then dried and packaged. But pink salt doesn't always end up on our plates. A significant portion is hand-carved into blocks, plates, bowls, and lamps. These creations pass through specialized workshops, where saws with reinforced blades cut the material, continuously cooled by water to prevent overheating. Craftsmen then polish each piece to reveal its inner veins and enhance its color, transforming a simple mineral into an aesthetic object. Other factories produce bath salts, scrubs, or massage stones, capitalizing on the wellness image associated with this product. While science remains cautious about its true benefits for the body, its symbolic and visual value is undeniable. From grains enhancing a dish to lamps illuminating a spa, pink salt has achieved a remarkable feat from prehistoric marine fossil to a contemporary icon of natural luxury. Today, Himalayan pink salt is much more than just a seasoning. It's a real brand, a product that, thanks to marketing, has surrounded itself with an almost magical aura. It's attributed with various virtues, including improving circulation, reducing stress, purifying the air, balancing the body's pH, and even protecting against electromagnetic radiation. But what does science really say? From a chemical point of view, this salt remains sodium chloride, like any other. 98% of its composition is identical to that of table salt. The remaining 2% corresponds to trace minerals such as iron, calcium, and magnesium, responsible for its distinctive color and taste. However, these amounts are so small that they provide no significant nutritional benefit. Despite everything, the narrative surrounding it has been enough to transform it into a symbol of well-being and naturalness. It sells not only for what it is, but for what it represents: purity, antiquity, mysticism. And in a world obsessed with authenticity and naturalness, this is priceless. In Pakistan, a kilo can cost less than $1, but once packaged, processed, and exported, it can sell for 10, 20, or even 30 times more in Western stores. As for derivative products, lamps, artisanal salt shakers, and wellness accessories, they sometimes reach even higher prices, especially when they are accompanied by concepts like energy, relaxation, or purification. In short, the true strength of this salt lies not only in its taste. It lies in its history, its aesthetics, and the marketing narrative that surrounds it. It's the perfect example of a prehistoric mineral that, thanks to a captivating narrative, has become one of the most coveted salts on the planet. But beware, that's not all. The rest of this video will be just as exciting. So stay tuned until the end. And most importantly, don't forget to like, subscribe, and hit the bell so you don't miss any of our upcoming content.
A single train wheel weighs several tons, yet it rolls smoothly on the rails for decades. A single rail, stretching 100 meters and weighing over 6 tons, can withstand tens of thousands of heavy loads without deforming. How does the steel industry manage to create such extraordinary strength? Few people realize that to forge a rail capable of withstanding such immense pressure, metallurgy must follow a long chain of complex processes. Iron ore is extracted from deep within the earth, mixed with coke and other additives, then fed into massive furnaces at extreme temperatures. From there, the incandescent molten steel is refined and rolled with millimeter-perfect precision into its distinctive head, web, and base profile. It then undergoes heat treatment and is welded into continuous lengths, stretching for hundreds of meters, before undergoing rigorous laser, X-ray, and ultrasonic inspections. In this film, we will go inside modern steel mills to witness the transformation of raw ore into strong rails. The global market for rail steel. The railway industry is not just a vital link in transportation, but also a massive economic sector. The global market for rail steel was valued at approximately $15 billion in 2023, and forecasts suggest it could reach nearly $20 billion by 2032. These figures reflect the scale of investment flowing into railway networks, particularly in regions with rapidly developing infrastructure like Asia, and even in the United States, where modernizing over 225,000 kilometers of track is considered a strategic priority. From a production standpoint, the scale is even more striking. The world produces about 1.9 billion tons of crude steel every year. In the United States alone, steel mills maintain annual productions of millions of tons, with a significant portion shaped into rails for domestic use and export. These rails are not an ordinary product. They must endure more than 20 years while withstanding the immense and repeated loads of trains. In many ways, each rail acts as a lifeline of modern infrastructure, ensuring stability, safety, and efficiency across the rail network. Raw material extraction and processing. A rail's journey doesn't start in a factory, but deep within the earth. Its most important ingredient is iron ore, and to reach it, immense open-pit mines are carved into the landscape. Here, hydraulic shovels as tall as 3-story buildings and ultra-heavy-duty dump trucks work tirelessly. Each bucket can lift tens of tons of rock in a single scoop. But before the machines can move, engineers must first drill holes that plunge dozens of meters into the ground. Centimeter-perfect precision is required because these holes will be filled with industrial explosives, and the blasting itself is far from random. Each charge is carefully calculated so that thousands of tons of rock are fractured, but the ore inside remains intact. Once the dust settles, the trucks and shovels get back to work, hauling the ore to the primary crushing station. In some geological areas, extraction takes place underground inside reinforced tunnels. The ore is scraped, loaded onto conveyors or small rail cars, and transported to the surface. Machines provide the power, but people remain the brains of the operation. They calculate explosive charges, guide the machinery, monitor safety, and inspect each load of ore. Every ton that comes out of the mine is far more than just broken rock. It's the foundation of steel, and ultimately, of the rails that will transport trains safely for decades. Once the ore is extracted from the mine, it can't be used right away. The massive blocks of rock must first go through an essential step, crushing. Inside processing plants, powerful steel rollers and hammer mills work continuously, breaking down blocks weighing tens of tons into small uniform particles. The size of these particles is not an accident, it's tightly controlled. If the pieces of ore are too large, they won't melt completely in the furnace. If they are too fine, the mixture becomes unstable during mixing. Only when the ore reaches the precise size required can it be moved to the next step, where it is blended with coke and flux materials in enormous mixing chambers. Gigantic paddles spin relentlessly, ensuring that every grain of ore and additive is evenly distributed. This step may seem simple, but it is critical. It guarantees that the mixture's chemical composition is balanced, laying the groundwork for steel with the strength and durability a rail demands. From these carefully prepared particles, the transformation to steel begins, a process that will ultimately produce rails strong enough to support the weight of trains for decades. Steel manufacturing. When the ore has been finally crushed and blended in the right proportions, the journey enters its most critical phase, steel manufacturing. This is the very heart of the rail production process. Inside the plants, gigantic electric arc furnaces and blast furnaces roar at temperatures of over 1,600 degrees, hot enough to transform iron ore and additives into a uniform flow of molten steel. Automated feeding systems measure each batch with kilogram-perfect precision, while thermal sensors and spectrometers constantly monitor the chemical composition. Heat-resistant robotic arms stir the mixture and remove impurities that rise to the surface. At this stage, alloying elements like manganese and chromium are introduced at the right time, enhancing the rail strength, wear resistance, and ability to withstand extreme loads. A modern electric arc furnace can melt over 150 tons of steel in less than an hour, but this power comes at a cost. The steel industry alone emits nearly as much CO2 each year as the entire aviation sector. This raises a difficult question. How can we continue to build the infrastructure the world needs while reducing the industry's impact on the environment? The result of this stage is molten steel of the highest quality, ready for the next transformation. Only when temperature and composition are kept under precise control can these steel backbones be created, strong enough to serve as the rails that will transport trains for decades. Shaping and forming process. After leaving the furnace, the molten steel is cast into billets and sent directly to the reheating area. This step is critical for stabilizing the metal structure before rolling begins. Inside massive heating chambers, the temperature is maintained at optimal levels, typically above 1,200 degrees. High-power burners work in tandem with infrared sensors that constantly scan every point on the billet surface, ensuring the steel doesn't cool too quickly. Even a slight temperature drop could harden the surface, leading to cracks or warping during rolling. Once stabilized, the billets move to the rolling preparation line. Here, enormous heat-resistant rollers, driven by robust hydraulic motors and gearboxes, begin to shape their length and cross-section. The system is programmed to refine the pressure and rotational speed for each pair of rollers, distributing force uniformly and preventing localized stresses. What makes this step remarkable is the seamless integration of mechanics and electronics. A central control computer collects real-time data from dozens of sensors and instantly adjusts the process. Every movement aligns perfectly, like the gears of a precision clock, producing billets that are elongated, flattened, and ready for the final shaping process. As soon as they leave the reheating furnace, the incandescent steel billets are fed directly into the rolling line, the final shaping stage before cooling. On a system of heat-resistant roller tables, the billets enter the roughing mill, where massive alloy steel rollers, with large diameters and smooth surfaces, press them with thousands of tons of force. The thickness is significantly reduced, while the length is stretched, preparing the billets for precise shaping. Next, the billets pass through intermediate stands, where the profile gradually takes shape. Here, the rollers are arranged in alternating positions, compressing and twisting the steel to evenly distribute stress and eliminate dimensional errors. In the finishing mill, rollers with specially designed grooves begin to sculpt the rail's classic eye-shaped cross-section, a design that offers remarkable strength while keeping the weight manageable. Between each rolling stage, high-pressure water jets cool the surface, removing the oxide layer and maintaining temperature stability. Along the line, laser sensors constantly measure height, width, and straightness, sending real-time data to the central control system, which adjusts roller gaps and speeds with extreme precision. One of the remarkable features of this process is the ability to quickly exchange roller sets, allowing plants to switch between different rail profiles without stopping production. This step is decisive. It sets the rail's geometry and ensures each piece meets the required standards before moving to cooling and heat treatment. Heat treatment and welding. Under the intense heat inherited from the rolling process, the steel rails still glow red and contain significant internal stresses. Cooling and heat treatment are the critical steps that stabilize the product's backbone. Immediately after leaving the rolling mills, the rails pass through a high-pressure water spray system, where a dense mist envelopes their entire surface. The speed and volume of the water are tightly controlled to ensure uniform cooling over the entire length, preventing warping or cracking. After this rapid quenching, the rails enter the heat treatment zone, where reheating furnaces are precisely programmed to perform processes such as quenching, tempering, or annealing, depending on the desired mechanical properties. The combination of immediate cooling and subsequent controlled heating not only enhances strength and durability, but also ensures that the rails retain their distinctive eye-shaped profile, with sharp edges and clean lines. This step is what guarantees that the finished rails can withstand the enormous repeated loads of rail traffic, while maintaining long-term stability. By carefully balancing temperature and time, engineers give each rail the resilience it needs to reliably serve for decades on some of the world's most demanding infrastructure systems. Fresh from heat treatment, the rails move directly to the welding line, where individual sections are joined into continuous lengths. Guide rollers work in tandem with laser sensors to ensure the rail ends align with absolute precision. A high-power arc welder releases intense heat, melting the steel edges while hydraulic pressure forces them together into a seamless bond. Immediately after, an automated grinding system smooths any excess material, leaving the weld surface perfectly level with the rail body. The entire operation is supervised by a central control system, which constantly refines variables such as temperature, pressure, and timing. The result is a joint so strong that its durability matches that of the solid steel itself. This process of welding long rails transforms shorter segments into continuous tracks stretching for hundreds of meters, rails that will carry high-speed trains with minimal vibration and with a strength built to last for decades. Quality control. The finished rails move to the quality inspection area, where every detail is scrutinized with precision. Optical sensors and high-speed cameras scan the entire surface, capturing images at a level that can see through the slightest scratch. The data is then processed by advanced image analysis software, detecting any deviation in shape, color, or texture. At the same time, ultrasonic devices and X-ray scanners probe deep inside the steel, ensuring there are no hidden defects, such as internal cracks or gas pockets. To complement these scans, randomly selected samples are subjected to rigorous mechanical testing. Powerful machines stretch, compress, and press the steel, while hardness testers measure resistance to deformation. All results are carefully recorded and stored, allowing each rail to be traced back to its production batch. Only those that meet the entire set of criteria earn the seal of approval, confirming they are fit for service. Once certified, the rails are cleared for packaging and distribution, ready to be shipped to construction sites, where they will become part of the railway lines of tomorrow. Transportation and installation process. From the factory, the rails are transported to the construction site on oversized trailers, securely fastened to prevent shaking or bending. Once on site, the steel sections are unloaded by cranes and specialized forklifts and placed in the designated preparation area. From there, the work that requires human skill and experience begins. Installers follow structural drawings to position each rail using laser levels and surveying instruments to control alignment and slope. Temporary joints are first secured with bolts, before being permanently welded or clamped. Throughout the process, workers constantly communicate via radios to synchronize their actions and ensure perfect connections. Machinery primarily assists with lifting and holding the rails, while fine adjustments, alignment, and finishing depend almost entirely on the skill and coordination of the installation team. It is this meticulous work that determines the stability and safety of the entire rail system for decades to come. Under protective coatings and solid welds, each steel structure is the result of hundreds of hours of work, combining the power of machines with the hands of skilled workers. From the mine to the construction site, each step contributes to creating the backbone of bridges, factories, and towering skyscrapers. By looking at this journey, steel reveals itself to be more than just a material, it is the foundation of modernization. If you like this video and want to discover other impressive manufacturing processes like this one, don't forget to like, subscribe, and hit the bell so you don't miss a thing.